Okay, no, like, come on. Like, I'm giving you the opportunity to ask all the questions. Take advantage of that. So 9C, guys, listen, if I didn't say 9C, we wouldn't be going over it. You need to ask those questions. If you have a question, ask it so I can answer it and I can improve your understanding. Because I didn't say something. And listen, eventually I'm going to stop saying, hey, I think we should look at this one, because you are juniors in high school. You got to advocate for your learning. You got to advocate for what you don't know so that you can improve that understanding. When you get to college, which y'all are only a couple years away, I know sophomores here next year, but when you get to college, no college professor is ever going to say, okay, now I see that a lot of us miss 9C, we need to talk about this one. No, you have to go to like their office hours or talk to your friend to figure it out. You've got to advocate for your learning. You got to ask. When you're stuck, ask a question. And that's not, like, I will say this, I feel like I know a lot of stuff, but I cannot tell you how many times I was the most frequent visitor to my college professor's office hours. Because I wanted to learn and understand, so I went and asked questions. That's why I learned as much as I did. I had a couple of college professors even say, I feel like you have a decent understanding of this, like, how do I get the other people who really need this to come? Like, you got to have a decision and a choice and a desire to learn. So please ask those questions. All right, so number 11, plot a fraction on the exponential graph, and 9C. So, it helps when I have this turned on. I have already scored these, right? So I have feedback. If you want to write any extra notes, please go for it. If a question pops up before I finish going over this demonstrated understanding, please ask it. But small notes about demonstrated understanding. If you also want to come during advisory or before school and ask more questions because you're still confused, please go for it. Quick question, can I get a volunteer for tomorrow's Hero Friday? Like, I think we're only going to be in here a couple minutes tomorrow, right? Does that sound right? Because we're going to the pep rally. Does anyone know what time that starts? Because I haven't actually seen a time for that.
I think students get dismissed at 8:20.
Sweet, so that'd be just enough time to do a weekly reflection and a Hero Monday, or a Hero Friday. Huh?
Like most of us
So,
everything, we get dismissed at 8 o'clock.
yeah, but like most of us will be here. But I will be at least able to give you a weekly reflection that I would ask you to turn in on Monday. Any volunteers? Huh? Sure. Y'all gonna let Davian take all the spotlight? Too scared to share who is your hero?
I want to laugh.
That's true. Miles went last week. I appreciate you. Come on, guys. I just want to get to know you a little bit. Oh, you got it?
I want to.
Well, she can do what she can do.
All right. Thanks, Leah. All right, remember, if you want to send me a picture so that you can show a picture of your hero, go for it. If not, you can just talk about it. All right. So, remember, this demonstrated understanding was all about identifying functions, being able to identify relations versus, everything's a relation or versus a function, looking at the mathematical representations. I think for the most part, everyone was good on the mathematical representations. There is something I will tweak in the future about this demonstrated understanding to not take as much time. Because I thought about it afterwards. I should have just said, hey, identify what this group of relation or representations are, because it's one statement. They're graphs, they're equations, or algebra. I should have done that. That's my bad. But you live and you learn. Target here, hopefully for the most part we're able to identify linear, exponential, quadratic, or none of these. Guys, please be careful about the way you're justifying it, right? If you're looking at a graph and you say, hey, that graph has a multiplicative rate of change so it's exponential, but you haven't actually found the multiplicative rate of change, then you can't make that claim. You don't have that evidence, right? If I see an exponential curve, I know it's exponential because it's an exponential curve, not because I found the multiplicative rate of change. You cannot make a claim unless you have the foundation for it. And I think Mr. Javi and I made notes like that on some of these, so please be aware of it. You can find it and then claim that, but that's something to keep in mind. We really haven't done too much with identifying if relations are equivalent or not. We'll do that on future demonstrated understandings. Constant rates of change, I feel like I saw better evidence of being able to write equations. I know some of us still need a little bit of help with exponential. We'll look at that. All right, so 9C is what we said. So everyone was good through 1 through 3, 4 through 6. Felt like we know how to improve our understanding there. Okay, so 9C. So first off, be careful. I did have some people say, hey, 9C or 9 is not a function because there is no pattern. Well, does a function have to have a pattern that we see in the table? No. Go back to the definition, Jaden. What's the definition of a function? So each input maps to one and only one output. -2 only maps to 2. -1 only maps to 5. Every input mapped to one and only one output. That was very clearly a function, but let's look at this rate of change again. If you look for a constant factor, the first set here would give you 5 halves, the next will give you 11 fifths. Notice there is no constant factor. So I'm jumping a little bit, but I just want us to see the factor from here to here would be 5 halves. The factor from here to here would be 11 fifths. There is no constant factor. So for those of us who are saying, hey, it's exponential, it's not. We need to look at that again. This is plus 3. To go from 5 to 11, it is plus 6, 11 to 20, 20 to 32. And so that's not constant additive. But remember, there's only 2 functions with constant rates of change. What are the 2 functions with a constant rate of change? Linear and exponential, but we found a new one recently called a quadratic. Anyone remember what the rate of change for a quadratic was? Linear additive, right? When I look at these, the plus 3, the plus 6, plus 9, what's happening? You go from 3 to 6. 6 to 9? 9 to 12? So this is constant additive. So this orange, we need to be careful about this. We call this orange the rate of change. What type of rate of change is this? Yeah, the type of function that had a constant additive rate of change was linear. So this rate of change has to be linear, and we want to be careful with that linear additive because I've actually, and I know this sounds super nerdy and super dumb, but I've tried playing with this. I've tried to develop a function, or at least the equation for a function that would have a linear multiplicative rate of change. It's still escaping me. I'm playing with it still. But it's not multiplicative. I want us to be aware of that, right? It is a linear and additive rate of change. We comfortable with that idea? Does that make sense? Questions about 9C? You good with that, Davis? So don't forget, guys, I already scored these, already put feedback on there, but if you need to update any of your knowledge on that, you can write on this. I'm going to have to collect it in just a minute to make scans of it, but you're good at this point. Like, it's already been scored. Kristen was listening, and she's done. She's like, I'm over this, Mr. Kenny. All right, cool, we can move on. All right. Oh no, apparently I didn't put the last 2 problems in here. Not sure why not. All right, so number 11, I think, was the one that was asked for. So 2 things about number 11. And this part of the reason why we have this build-up up to this point. What is the very first thing we need to do in order to write this equation? What's the first thing we need to do, guys? We want to write this equation. Identify the what? Okay, hold on.
I said identify the y.
Okay.
I said the point and the
Oh gosh. I feel like y'all are skipping like 3 steps in. And see, this is what I want us to keep in mind. Yeah, am I going to need that y-intercept? Yes, 100%. However, we skip steps instead of like starting at the foundation to get us there. Why are you trying to find the y-intercept? Yeah, but how do you know you need the y-intercept? Okay, and how do we know that the equation is y equals a times b to the x? Remember, identify the type of function. Listen, I get it, that you're like, Mr. Kinney, I know it's exponential, I know that, and I know I need the y-intercept, but I promise you, learning the logical steps to get there is going to be really helpful, because we're doing only linear, exponential, and quadratic right now, but we're going to extend into cubic, we're going to extend into quartic, and quintic, and logarithmic, like we're going to go into all these other functions, and hopefully, if we have time, we're going to get into these things called sinusoidals. So we're going to build and build and build. And so we need to build strong foundations where we identify the type of function first, write out the formula for that type of function.
Teachers,
It's gonna
please
help us
pardon
go.
the interruption. Any student who signed up to take the ASVAB test should report to the library at this time. The test will begin in approximately 5 minutes. Thank you.
Okay? Anybody? No? Okay. So yeah, y'all are saying we need y-intercept. I'm in agreement. 100%. Okay. So what's my y-intercept? 4, right? Now, one thing I will point out is the a value is 4, but be careful. The y-intercept is not just a 4. Does anyone know why I'm saying that? It's a point, right? So what is that point? It's not just 4. It's 0, 4. And we need to be very careful about that, because when we study quadratics that we're really going into today and tomorrow, well, not tomorrow, today and Monday, when we talk about quadratics, the x-intercepts, the y-intercepts, the vertex, there are all these points that are really, really important. We have to address them as points. And so 0, 4, and so I do have part of my equation already. I have that 4, but what does that be? The rate of change, called a constant factor. So remember, we want to find that constant factor, right, my f. But, and I will say this, can you find it on the graph? 100%. But this is the key for me on exponential. What is the best representation to find that rate of change? Table. Do not forget, tables are your best friends when it comes to rates of change. They're the easiest. And so I already have part of the table. What's the first point on my table? 0, 4. 0 maps to 4. And I'm going to try to find a good point. I don't see any here. There's one. What's that point? 1, 6. And then here I've got 2, 9. And there's lots of different ways that, I won't say lots, there's a few different ways. You can guess and check here. There's a term for it called a common ratio that some textbooks, some online things will use. But to me, the easiest thing to recognize is that an exponential function has a constant what? Multiplicative rate of change, called a constant factor. So I'm going to take 4, I'm going to multiply it by f, and what does that give me? 6. 6 times f gives me 9. So 4 times f gives me 6. And at least that's where I'm going to start. I'm going to solve that equation. How am I going to solve that equation? Divide by what? So divide 4 by 6. And so this is one reason why I always like to write out the equation and be just being careful with it. I wouldn't even say just divide 6 by 4, because what I'm really going to do, and keep this in mind, the order matters. I'm not really just trying to do 6 divided by 4. What am I really trying to do over here? Get the f by itself, so I need to make this 4 a what? I need to make it a 1. When we're solving equations, we're either going to make a 0 or we're going to make a 1. Those are known as the identities, and we're trying to create those. So notice, 4 divided by 4 is 1. And whatever I do to one side, I do to the other. And so, Kelly, you 100% had the right idea. I just always want to emphasize that. I'm really trying to create a 1 on the left-hand side, and so then I do 6 times 1/4 for that equivalence, right? What I do to one side of the equation, I have to do to the other. That's the properties of equality. All right. And so 6 times 3/2 is also done. All right. So from there, Taylor, does that answer your questions? Yeah. Now, Bella, you were still asking about how we graph a fraction on here, right? So we can see very clear points along in here. But let's say I want to go backwards, right? For example, let's say I want to know the output when my input is -1. Right here. Well, that's going to be 4 times 3/2 to the -1 And you can just type that into the calculator. But I will remind you, we found out that a positive exponent indicates repeated positive exponents, or whole exponents, positive or repeated multiplication, whereas that negative integer exponent is repeated division, right? So essentially, I'm going to divide by 3/2 or just multiply by its reciprocal. And that gives me 8/3. Again, you can just type it into the calculator. I ain't sweating it. Now, to answer your question, Bella, if I'm graphing this, I'm just going to estimate. I know that 8/3 is between 6/3 and 9/3. You can also just get the decimal version of it. The reason I do that is because 6/3 is 2, 9/3 is 3. So 8/3 is somewhere between 2 and 3. It's actually 2.6 repeating. And so my x is -1, y is -8, or it's positive 8/3. So I go to -1 in the x, and I go up 1, 2, above 2, but less than 3. But it doesn't have to be perfect. It's just an estimate. I know it's between 2 and 3, so I'm going to just go a little bit closer to 3 than 2. If you want to, you can kind of mark off like the halfway spot so that you know if you're above or below it. But that's it. Don't stress it too much. Sound good? Okay. Other questions that have popped up as we've talked about these ideas? So we're going to be able to write these equations on our own in the future, yeah? Identify each of the types of functions, know if it's a function or not, yeah? Okay. Put your demonstrated understandings together in the center of the desk so I can make scans of these quickly. Okay. That's not what I want. There it is. Okay. At this point, we're going to go back to the Desmos activity. So notice, I don't know if I emphasized this yesterday, but you have a new proficiency scale that is all about what types of functions. Quadratic, but there's something else I said with them. That's right, functions with linear additive rates of change, also known as quadratics, right? Yeah. The defining characteristic of all quadratics is that they have what type of rate of change? Linear additive. And so there's these foundational pieces right here, okay? Identifying each form of a quadratic equation. Now, please hear me clearly on this. Foundation are supposed to be things that either you learned last year or that we've already covered this year. I know some teachers emphasize the different forms more than other teachers. So if you're not 100% familiar with all the forms, it's okay. That's why I have the activity that we do on Desmos. But these are the three forms: standard form, vertex form, factored form. We're going to explore all of those today. But hopefully the idea of a quadratic function, x-intercepts and y-intercepts, we have heard about and know something about. Okay? We're going to make sure we formally understand some more of those details. But here, this is the target, right? We're going to use Desmos to learn about the key features highlighted in vertex form, factored form, and standard form. Each form has its own key details. That's what Mr. Hobby was talking about yesterday, right? And we need to figure out which values those are. Just like when I say f of x equals mx plus b, m has a very specific meaning for that linear function, right? That's the what? Slope. That's the rise divided by the run. The change in y divided by the change in x. That b has a very specific meaning. What is it? The y-intercept, right? So we need to learn what the different pieces of those equations mean. So hopefully it's not terrible. Hopefully it's something we remember. But we are talking, and then we're going to get into, after that, converting from factored to standard form. This is the last real thing. So today is the last lesson with new concepts. Everything else will be practice with it, making sense out of it. So be planning for a test next Thursday or Friday. That's what you should be thinking about. So notice I'm giving us almost a full week on just this information, okay? If we are crushing it, maybe before then, but my guess is Thursday. All right, so one thing I want to point out, we will tear these pages out of the book later. But true to form is the lesson from the book that we are using. It's all the forms of quadratic functions. They have it all in one lesson. And so they have it laid out here of standard form is this, factored form is this, vertex form is this. And it just asks us to identify all the different characteristics that you already know. Do we remember those different characteristics, or do we even recognize all three of those forms? You want me to turn the lights off so you can actually see it better? My bad.
Yes.
Do we recognize all three of those? It got dark. Tastes good? Is that so you can fall asleep easier?
Yeah.
Do we recognize all three of those forms?
Yeah.
Yes? You don't recognize the second one? Do we remember what A, B, and C all do for that standard form? Like how they affect the graph?
A, like the concavity.
Oh yeah, we looked at that yesterday, right? What did A determine? The concavity. When was the parabola concave up? When A was positive. And so A was negative, that parabola was concave down. Okay, cool. What about B and C? Do we remember those? I know, I meant from last year. Do we remember those? No, so you remember vertex a little bit? What do you remember about vertex? I mean, all of these are parabolas, right? They're all quadratics. By the way, how do I know all three of these are quadratics? The x squared, right? I literally see an x squared right here, yeah? Now, I don't see x squared here, but how do I know it's there? Distribute, what's x times x? X squared. Okay, and then again, x minus h squared, that's x minus h times x minus h, so I got x squared again. But these are all quadratics, all parabolas, right? But do we remember what a, h, and k all do in that vertex form?
Don't K, it kind of where across the Y.
Something about the y.
Like,
So, all right.
have a flick.
Okay, so this is why we're doing the Desmos activity, all right? So let me clarify that. I just want to see, like, this Algebra 2 textbook and correctly assumes that we know these three different forms. I know we need some practice with it and exploration. So that's what we're going to spend the vast majority of today on. We'll tear some pages out later, though. All right, so right here, I need us to get back to our vertical surfaces. Actually, I need you to, one person per group hopefully has a iPad, yeah? Okay, let's do this. Everybody who has their iPad, which we should all have our iPad, everybody who has an iPad, get it out. Go to student.desmos.com, log into your Desmos account, and enter that code just so that you can have access to it later. If you don't have it, plug it in. Okay? So, log in. If you don't, I'll forgive you.
What,
For now.
everybody needs to?
I got this. Is it USB-C? Yeah. You can ask Miss Williams if you want to cross there and ask her if you can plug it in for a little bit. So, just throw that code back up there. There it is. So remember, by the way, log into your account. Make sure you're logged into your account so that you have access to it. Because once you logged in one time, you can always go back to it. I hear it. Thank you. Hey. Oh. Okay. Sounds great. Thank you. All right. We all logged in? No? Do we have? I'll write the code up, because we gotta get going. Alright, so there's the code written on the whiteboard, if you need it. Alright, so we already talked about, let's see, A, right? So we looked at the fact that as we change A, what does that do to the standard form? So A is positive, so it's concave up. A is negative, so concave down. Now, what I need us to do is to move to slide 4. And what are we adjusting in slide 4? C, right? So adjust slide C, play around, figure out what slide C does to that parabola. So I need us to get up to our vertical surfaces. Remember, sorry, one person per group has an iPad, don't forget. Y'all are just logging in so that you can have access to it later. But one person per group has an iPad. Manipulate that C, come up with a conjecture for what it does, move to the next slide, okay? Once you move to the next slide, write up your conjectures on the vertical surfaces. I'm going to go make scans of our demonstrated understandings during this time. Questions about what to do? Alright, well, I shouldn't be too long making scans, but if you finish early, just continue on to the next slide. Let's keep going. Don't sweat. Alright, so let's talk about it. So, y'all can scoot away from the board a little bit or move to the center of the room and look at the board as I talk about this sum. Okay? So how does the value of C explicitly connect to the graph? That's the question I'm asking. There's a lot of us that are talking about the vertex, and I will say, changes in one feature of the equation will change other parts of it, right? C affects the vertex, sure, but what part of the equation, let's see if I can get a little bit, there we go. What part of the equation explicitly connects with the graph? What's my C value right now? When I say explicitly, by the way, what do I mean by that? Say again. No, so explicitly means it's approximately, or really approximately, the same. But what is C right now?
2.5.
2.5? Negative 2.5? Anybody see any points that y'all have referred to that have that negative 2.5? Say louder. The y-intercept, right? The C is not, it's kind of affecting the vertex, but what is C? It is the y-intercept. We see that now? Okay? Whatever C is, that's what your y-intercept is. If I change my C to 5, what's my y-intercept now? Oh, you can't see it. 5. If I change my C to 14, what's my y-intercept going to be? 14, okay. So let's put that into our notes on the Frere model that I gave y'all. Let's update our understanding and move on to the next set of slides where we are actually going to apply and practice some of these ideas. Alright, so let's talk about it. Drake, you made a very important observation when you were talking about A with your group. What did you notice about the A here?
It still controls the concavity.
It still controls the concavity. Did y'all see that as well? And we want to be careful about our language, because one group I saw made the same mistake a lot of students make. They talked about if the parabola is positive or negative, things like that, but it's not about the parabola being positive or negative, it's about the A, right? If A is positive, that parabola is going to be, if A is positive, the parabola is concave up. It's not just up, it's concave up, okay? And if A is negative, the parabola is concave down. And so I know that sometimes we need like a connection to kind of help us remember that. Hopefully positive makes us think up, but like if things are looking up, they're what? Positive. Like in your life, if things are looking up, that's a what? Positive, right? If things are looking down, that's a negative. But also on top of that, concave down like a frown, and that's a negative idea, right? Any questions about concavity on this one, though? Now, there's some debate about R1 and R2. What did R1 and R2 control? The x-intercepts? Is that right? Yes? Everybody saw that? So at one point, I see y. So several of us have y-intercepts, and I say y'all have R2 as the y-intercept. Why were y'all thinking R2 is the y-intercept? Is that what y'all are seeing still? Notice how you said shift over, right? If you're talking about over, left and right, what direction is that? That's x, right? Notice how they're both r's. The reason why they're both r's is because they are the same in a lot of ways. Notice it's x minus r1 and x minus r2. What's R1 and R2 with inside those parentheses and what? What's inside those parentheses with R1 and R2? And X, right? Okay. And so when we talk about R1 and R2, they are X-intercepts. One thing I want to point out, and I want y'all to notice clearly, or I want to make clear, when we say R, the reason we use the letter R is because it's known as a root. Okay? The root explicitly connects to an intercept. Okay? So when we say R1 and R2, those are the roots or the X-intercepts. Although I do have to say, when I say R1 is an X-intercept, that's not quite accurate. Does anyone know why? I think someone talked about it. We have a key over there, idea over there with the 2's. What did they say? What did the 2's say about those X-intercepts? Say it louder. The Y is 0. Is that important to include with X-intercepts? Remember, with a Y-intercept, the input was what? 0. But with an X-intercept, the right? We want to be clear about that language. Here, one thing I do want to ask is, does that confuse anyone? Like, why in the world that would happen? No, we just accept it? We just assume that's right? You just accept it? Well, how did we know in the standard form that it made sense that C was the Y-intercept? The X was 0, so what do? We substituted it in, right? Notice I do use that more mathematical language there. We substituted it in. So what can we do here with these X-intercepts? Substitute 0 in for what? Oh, which one is it? With an X-intercept, what is 0? The Y, or the output, yeah? So when I look at, I'm just going to do it over here. Boop. Wow, that was way too close. Okay? When I substitute 0 in for Y, there we go. What I want us to see is this. And hold on to this idea. I'm not testing you on this yet, but it's going to help you a lot in the next unit. If I am multiplying things and their product is 0, does anyone know about something about those things that we're multiplying? There's got to be a 0 in there. Where does there have to be a 0? Okay, let me ask this. If I have 0 equals A times B, what do you know about A and or B? One of them's got to equal 0, right? The only way to get a product of 0 is if you multiply by a what? A 0, right? So either A is 0 or B is 0. And so now, I'm multiplying these things, right? So either A is equal to, or X minus R1 is equal to, or X minus R2 is equal to, and I can now solve these equations. Notice, what does X end up equaling here? R1. And so the X-intercept is R1, comma 0. I do want to point out, notice how it was X minus R1, but R1 is R1 positive or negative? Notice I had to add R1 to both sides, didn't I? So R1 is now positive. And so we want to notice that the roots are actually the opposite of what we see there. So if I have X minus 3, what's my actual root? If I have X minus 3, what is the actual root? I was going to say, we just said it needs to be the opposite, didn't we? So if I have X minus 3, what is my root? R1 is 3, positive 3. If I were to have X plus 2, what's R2? Negative 2. Because when I set it equal to 0 and I solve and I use those inverses, I need the opposite. Or I would get the inverse. Okay? First off, do we see that A is controlling the concavity? R1 and R2 are controlling the roots or X-intercepts. And Y would be the opposite for R1 and R2? Does that make sense? So what I would do if I were you is I would update my notes on, hold on Bella. Remember, what form did we just look at? Factored form. Remember, I gave you a different Frere model for each form, right? You just did standard, now we've just done factored. So I would put these notes on factored form. I would write out that formula for factored form. Update your notes, and then I want you to do the practice that's on, like, I don't know, slide 7 or 8 or so, somewhere in there. My answers, maybe with a graphing calculator, type those equations in. See if we're getting them right. That's a great question. Why don't we graph that equation, see what it says on the graph. So you have graphing calculators, yeah? Well, then you better learn from Landon here. Really quickly, I would hit menu and I would go to Zoom Standard really quickly, number 4. Zoom Standard is number 5 there. Yep. Now do that graph. Have y'all checked your answers yet? Huh? Say it one time. Oh,
It's an X minus 3, that's a parentheses, and then that's,
square?
yeah.
Mm-hmm.
Wouldn't that be that 2 times?
It's a great question. Let's find out. All right, if I can get y'all to move to the center of the room, let's talk about these 4, because there's some good ideas to talk about here. All right, first things first. I did kind of hint at it early, so y'all had a little bit of an advantage, but y'all did the best out of any class I've ever had at recognizing these x-intercepts, okay? First off, I think we're all comfortable with concavity, right? Up, down, down, up. We all good with concavity on this one? Okay? But the x-intercepts, a lot of times the most tempting thing to say here is -3, 0, and 7, 0. But we just talked about that form, a times x minus h, or sorry, not h, x minus r1 times x minus r2. And so we need to remember, and I mentioned this earlier, we need the what of this value here? Opposite. Remember, if I set this equal to 0 for my zero product property, and I set x minus 3 equal to 0, what do I do to solve for x?
You got to inverse, but 3.
And so my x-intercept would have been 3, 0. Notice how I needed the opposite of the x minus 3. So I need the opposite of this plus 7. One thing I do want to point out about why this is true, just to help this make sense, notice if I substitute 3 in, what's 3 minus 3? So you see how that's going to make it 0 right here? If I put in -3, does that make it a 0? No, I need the opposite so that this becomes 0. In the same way here, I would need a -7 so that here, in this factor, what do I get? A 0. So I would make the note and make sure you understand that, and maybe put an example in your check your understanding / your notes. R1 and R2 are the opposite of what we see inside those parentheses. R1 and R2 are the opposite of what we see inside those parentheses. Once you have those notes updated, please move on to slide 12. Please note when we look at slide, oh wait.
But what you say, R1, R2?
It's going to be the opposite of what we see inside of those parentheses. Like show an example of one of these, right? The x minus 3. Oh, we still need to talk about the last one too. That's a great explanation of why. I would probably make that note of like, draw an arrow, set it equal to 0, draw an arrow down showing the 0 product, and make the note of 0 product property. Because it's not just like we magically get to equal 0, it's because we're multiplying, getting a product of 0, right? So yeah guys, don't forget, it's not something magical. It's literally because we're using that 0 product property. That's why we have the opposite there and why that's all working, or how to identify those roots. It's not magical, right? It needs to set be equal to 0, and then we're using that 0 product property. That's why the roots are the opposite. Okay. I do want to move a little bit quicker through this last one, so I want to make sure we get it done since I will not get the chance to teach y'all tomorrow. Really quickly, I want to note here x minus 3 squared. Does anyone know another way to rewrite that to make it easier to see what my roots are?
Split x minus 3.
Isn't that going to be equivalent to x minus 3 times x minus 3?
Yeah.
And so now I can clearly see both of my roots are just what? Both of my roots are 3. 3 comma 0, 3 comma 0. Those are my roots. Okay? So y'all were picking up on that pretty well. Once you have your notes, move on to slide 12 and then continue. This next set is all about the last form of a quadratic. What is that last form? Vertex form. F of x equals a times x minus h squared plus k. One thing I want to remind you as you work through this one, mathematicians are not original. They name stuff because that's what it is. So if we're talking about vertex form, there's something you should be thinking about with that parabola. Let's get to our vertical surfaces and explore it and not play games. To unfortunately be at a pep rally, not unfortunately, good for the pep rally, but unfortunate for our learning side of things. I am going to record right there if y'all can scoot to the side. So once again, what does A do? Like A is not original. What does A do? What does A do to this graph? It changes the contact cavity. If A is negative, the parabola is concave, and if A is positive, the parabola is concave up. Has that changed? Will that change? No. Guys, the reason why we use A all the way through is because A is the only thing that's the same in every form. Right? By the way, we're on vertex form. You have that as well. But I want to talk about more the H and the K. So when I look at H, y'all started to pick up on this, right? Look around the room. What is H controlling? The x value of the vertex. What is K controlling? The y value of the vertex, which is why we call this what form? Vertex form, because we can easily see the vertex, right? I do want to point out, if I were to ask you then, what are the coordinates of every vertex in vertex form, how would you write the coordinates of the vertex? Right? They're points, yeah? Okay. So what am I going to put here for the x value of the vertex? Y'all had it. Move around the room. What did y'all say the x value of the vertex is? It's h. So what's going to go right here? Oh. What's going to go right here? Okay. That's the vertex, guys. The vertex is quite literally h comma k, the x value of the vertex and the y value of the vertex. That is where it's coming from. That's why we call this what form? Vertex form. It's not a mystery. Make sure you write out the equation for vertex form. A times x minus h squared plus k. The unfortunate part about quadratics is you're going to have to learn 3 forms just for the quadratics. Make sure you go ahead and start studying this. By the way, Lyndon, I got 2 more really important things to point out, so don't pack up yet.
I'm not.
Okay. Just looks like you were. My bad. Okay. What questions do you have about those details? Okay. Now, I don't know how many of us got there, but I do want to look at this. What is that purple line that I have drawn through or graphed through the parabola?
Line of symmetry.
Line of symmetry. Does anyone know another word we use for that line of symmetry? Starts with an A. It's also called an axis of symmetry. So lines of symmetry are also going to be called axis of symmetry or axes of symmetry. Just be aware, because I use axis of symmetry because that's what I grew up using. And so I just accidentally say it sometimes. I usually use line of symmetry. So what affects the line of symmetry? Is A changing that line of symmetry? No. Is H changing that line of symmetry? So does that, as I move H, does the line of symmetry move? Oh, definitely yes. Like, look at it. Does K move that line of symmetry? So what is the only thing that affects the line of symmetry? H. Now I need y'all to pay attention to this, because when we are talking about equations of line, I think I mentioned, or vertical and horizontal lines, I think I mentioned this yesterday. Does anyone know what the equation for this line of symmetry would be? Okay, let me ask you this. What's the same all the way through? What is that -5? That's the what of each of those points? That's the x value, right? So it doesn't matter what y is. What is x? X is... That's the equation for that line of symmetry. No matter what y is, x is equal to what? -5. Okay. What about if I change my h now? By the way, what is h right now? -5. What if I change that h to 6? Or 4? What is my line of symmetry now? Thank you, there we go. It's a line, right? X equals 4. So what is the equation for the line of symmetry? X equals h. That's my line of symmetry. Okay? Whatever x is equal, or whatever h is, that's my line of symmetry. Now we're going to have to do some more work on Monday for sure, but I want to talk about a couple of things, because the whole point of this is we should be able to sketch a graph based on identifying these features. So what would the vertex for this function be? It'd be what?
Is it 3 or -3?
That's a great question. What do you think?
-3.
Remember when we had R1 and R2, how we needed the opposite? Because it was x minus R1 and x minus R2. So because it's x minus h, I need the opposite. So this is going to be a what? +3, and the y-intercept, or the y value of the vertex is 4. My line of symmetry is going to be x equals 3. Is it concave up or down? So if I wanted to, all I have to do is take those features, and there is my vertex, there's my line of symmetry, and it's concave up. Is that the most accurate graph in the world? No, but that is the graph based on those key features, okay? You have enough right now to be able to do all the check your understandings for the mild and the medium. We have not learned the spicy stuff yet, especially because you have an extra day and we're losing a day. I need y'all to attempt those check your understandings before Monday so that we can learn the spicy stuff. Yes, I already made scans of that.